So it's good to welcome Pranav back to IISc after several years, though it is still a virtual meeting. Pranav was a undergraduate student in our BS research program, and after that he went to Princeton University where he did his PhD, and after the PhD, he has joined this startup company called Q-Control, working on quantum algorithms on noisy processing machines which are being constructed, and he has interesting results to present. I remember that even in his undergraduate days, Pranav was always interested in making something new, and he made a portable device for detection of malarial parasite, and he was happy to show the prototype that he had to me and to others at IISc, and he has been inquisitive in that way to combine both theoretical and experimental results, and we will hear some of it today from him. So, okay, Pranav, over to you.
Thank you for the kind words. So today I'll talk about how we can use optimal control or robust control to improve algorithmic performance on quantum computers right now. So this is a rough outline of my talk. I'll start with a brief intro of what Q-Control does. And then, as you know, the two key elements we need for universal quantum computing are single qubit gates and an entangling two-qubit gate. I will show two ways of tuning such gates up. I'll start with a model-based design of such robust gates for single qubit gates, and I'll show an example of closed loop optimization for two qubit gates. Finally, using all these results, we will combine it with compilation and better error mitigation to get algorithmic improvements on superconducting devices. So control has often been critical in starting new industries. It was essential for aerospace, been essential for robotics, and even autonomous vehicles. It is very important. And at Q-Control, our mission or our thought process is similar. Our goal is to use control to improve quantum technology and make it useful faster than it would normally be without control. So Q-Control solutions typically work on, they are very hardware agnostic, and we have tested them on various superconducting circuits platforms, trapped ions, NV centers, and they also tested them on quantum sensing schemes. We have a pretty large team of quantum control engineers spread across the world, more concentrated in Sydney and LA. So if you think about the full stack of quantum computers, you would have the bottommost hardware layer, followed by some firmware layer where you would do gate characterization, a tune-up, or any hardware level operations. On top of that, you need some hardware aware compiler, and then as you go up in the stack, you go to quantum error correction, compilation, and at the end you end up to applications which the user would see. So we focus on mitigating error and suppressing it at various stages in the stack. So typically, with like the two tools which I would like to highlight are one tool called Boulder Opal. It's focused for physicists and quantum computing engineers, where we really want to understand what is, like, characterize the hardware, simulate the system, or do pulse level gate tune-up. And then the Fire Opal is focused more for computer science community who have a lot of interesting algorithms, but might not have the know-how of the fundamental physics going on at the hardware stack. So Fire Opal essentially takes care of all the tune-up, includes error mitigation for measurement and Crosstalk aware compilation all into one package, so it's very easy to use. With these results, we have, with these tools, we have seen pretty good results on real hardware. Primarily superconducting circuits is what I'm showing here. We see typically at least 10x improvement, you might say, in performance. The gate or the tuned up gate stays pretty good for longer time. The speed of tuning it up is also much faster than traditional methods, and we get pretty big. All these 10x's add up, and you get much bigger improvement on algorithm success probability. And all these things are very easy to use. They are all written in Python, and it's typically quite straightforward to, once you log on to the system, to quickly incorporate in your lab or your experiments. So in Boulder Opel, as I was mentioning, it's more about the hardware level, and this is what we will use to show the two results primarily of doing robust optimization of gate operations at pulse level itself. The key thing about this package is also that you can simulate quantum systems and dynamics much faster than QTIP typically. And also you can do automate many of these things, so it's much easier to use. So, okay, let's start with trying to tune up our single qubit gate. And also, please feel free to stop me at any point and ask questions. It is better to have it more engaging than me just speaking. All right, so yeah, so typically you would have some circuit with a single qubit and two qubit gates, and say you have this X gate. On hardware level, it would be implemented by a microwave pulse of this Gaussian shape. Essentially, there's some drag pulses, but essentially it's Gaussian shape. And IBM has done a great job with providing pulse level access to the systems. So our approach here would be, we would replace the pulse shape of this Gaussian with some optimal pulse shape coming out from the optimizer. And the requirement we would put on this pulse shapes, by what I would start calling robust pulses, is that they be robust or they be insensitive to fluctuations in certain device parameters. So how do we go about designing such robustness in optimization? So let's take a typical, let's say we want to tune up a gate G. After compilation, it will go into a schedule where Qiskit pulse will have some waveform for it. After that, it will go to the actual hardware stack where you have arbitrary waveform generator, various control lines, filtering, and everything. And in the end, it goes to the chip quantum systems here. Let me just start a point. Yeah. So typically we don't have much information about the hardware bandwidth limitations or how exactly the transfer function would be, but we can think about it at a high level in following terms. So let's say the control Hamiltonian we are trying to act for the gate is this HC as a function of time. And let's consider two noise processes. One noise process is typical dephasing, or let's say the frequency of your generators is jittering around. Let's call it eta t. This I would refer later as dephasing noise. And let's consider amplitude noise, where there's some fluctuation in the amplitude of your signals with time. And let's say typically we don't really know the exact distribution of these systems or the time scales, but the control that we have is essentially I and Q quadrature of your microwave pulse. So those are the two pulse shapes that we can play with. The way we would go about defining such a problem is that you would put in the Hamiltonian in here. You would put in the optimizable parameters, which are our I and Q quadratures. And one key important thing is to put in a smoothing filter. This is essential to incorporate the bandwidth limitations of the AWGs. Typically, I think right now on IBM systems, it is 4.5 gigasamples per second. But that is something one needs to be mindful of. And now the way we would bring in robustness is we'll create a noise term. In this, while generating this particular pulse, I created this dephasing noise term, which eta, which I mentioned earlier, where essentially for every iteration of the optimization loop, we will have a quasi-static noise term sample from some distribution, and then we will run the optimization. And at the end of it, this is the pulse shape that comes out. When we try it on the IBM hardware, so here on x-axis is the time. So imagine you chop up this pulse from 0 to a time t, and you at every given point you measure what is the excited state population, and you compare with your simulated expectation. You see a fairly decent agreement between experiment and the simulation. Now one might argue, okay, what about the small discrepancy here? Well, that discrepancy will resolve it by essentially what here we have assumed that the mapping of I and Q is identical. Basically the scaling of I signal and Q signal, but typically there is a small mismatch in experiment. So that would be a small tune-up which we can do quickly, and then you can get good results.
So now there is a question. Can you? Yeah. Vijay, go ahead.
Yeah. Hi, Pranav. If you could just go back one slide. I just want a clarification. See this first term where you have identified these noise processes.
This one.
You describe them as noise in the generator frequency. I mean,
this was the one for frequency. So eta is the one. I mean, noise frequency is an example. Like if there's like phase slips or something happening, but it could also be just a dephasing process.
But you actually mean to say this is the frequency fluctuation of the qubit, not of the microwave generator. I mean, usually the microwave generators are much more precise than the qubit. I mean, it's also written, as a coefficient to sigma z. This is not a control field, right?
You're absolutely right. But one thing I want to make here is by choosing microwave frequency, we try to be in the resonant frame of the qubit. So to me, as an experiment, I feel like they are equivalent because it's always relative. And you're absolutely right that phase stability of microwave generators is typically quite good in terms of like qubit lifetimes. But we often do this, like we have to average like many times these experiments, and then the phase stability over your whole average time becomes important too. So in some sense, if imagine that your phase shifted, then that can also contribute here. But you're absolutely right. I think dephasing is more accurate term, at least for all the like lowest orders. That is definitely the most dominating effect. Does that answer your question?
Yeah, thanks. Go ahead.
Yeah. All right. So how do these results come? How does this strange pulse shape compared to a typical Gaussian plus drag pulse shape that we often use in superconducting circuits. So on x-axis, I'm showing detuning of the drive carrier frequency. We can, I mean, this is one way of simulating how sensitive we are to detuning. Now, this detuning, as I was mentioning, is relative, right? Like, so it could be that we have just calibrated the frequency of the qubit wrong, or I mean, yeah, it's basically that, right? Like the difference between your drive carrier frequency and the qubit frequency. So what we see is IBM default pulses, Gaussian pulses, very rapidly become quite bad. This is just a simple X gate if the detuning is off. And of course here it's quite large detuning, almost like 3 megahertz range. But the point is that Q control dephasing robust pulses give pretty good X gate, even if there's some small mismatch in detunings. So one can imagine processes where if the qubit frequency is jittering around because of maybe coupling to some two-level systems or something, so long as the jitters are not too big, these kind of pulses would still do a good X gate without further calibration. So this is what I want to highlight is the robustness here. And one can construct such robustness for different parameters. So you could construct it for amplitude fluctuations too. And let's see how that behaves. So another thing is on a typical chip, so this is a 5-qubit chip, you would have variation in qubit frequencies. Unharmonicities are typically similar, but there will be some other crosstalk terms there. Here, what I'm showing is on x-axis the 5 qubits on this particular chip, and on y-axis are 4 days. Basically, what we do is we take the default calibrated gates on August 4th, and this is the error of the gate. And then we use the same pulse that we save on this day on 3 consecutive days, and you see that the quality of the gates deteriorates rapidly, and of course it depends on qubit to qubit. For some qubits it's not too bad. In fact, in this qubit it slightly gets better the next day, but typically there's a lot of fluctuation there. And whereas the amplitude robust gates or even dephasing robust gates, you can see that the color bar is much darker. Darker is lower error, brighter is more error. So here's the color scale. And here you can see that both these pulses are much better. And more importantly, they're quite homogeneous across the whole device and also over time. This is very important from algorithm point of view or even optimization point of view when we think about VQE optimization, because you don't want it's okay if the actual performance is slightly different, but consistency is quite important. So here we did X gates in sequence. So basically we calculated error for qubit 0 while all other qubits were idling in ground state, then do for qubit 1 and so on. Now another experiment you can think of is to do it in parallel. So what happens if you run a sequence of X gates on all the qubits simultaneously? Well, technically there shouldn't be any difference, because if there is no crosstalk, then they should be isolated. We are not trying to we have not done any 2-qubit gates. But what we see on this device is the moment you start doing parallel gates, the gate errors goes up tremendously, and it's all across the whole device. This is a clear sign that there is significant crosstalk term present. Typically in superconducting devices, ZZ crosstalk is quite common. But the point is the same amplitude robust and dephasing robust pulses that we saw 2 slides earlier perform pretty well. They are unaffected by this. And this is the message here, where here you can see almost that the gate error difference is over an order of magnitude. And this is one example how robust pulses can give you quite a big advantage in terms of individual qubit error rates, taking into account device-to-device variations, and also much better stability over time. So if there are no questions to that section, I'll move to 2-qubit gates now. Okay, so all right, so now that we have single qubit gates, that's all good. Let's try to get some entangling gates also. Why are entangling gates important? They are typically the key bottleneck right now for any algorithm, because single qubit gates are typically 3.9 or even 4.9 fidelity, while 2-qubit gates are 99% around that, at least on IBM systems. And that's also the typical record for large-scale systems. So it's very important that we get good 2-qubit gates with higher fidelity and more stability so that we can go towards error correction threshold. So if we use our previous approach here, where we assume the Hamiltonian for the system and we try to do model-based optimization, typically it's quite challenging because, so in this case, what I'm showing on x-axis is time, and y-axis is the population measured for different levels. The key message here is to see that, so this evolution is for a cross-resonance pulse. The lines are theory while the points are experimental data. The key message here is that you can see clearly in this region that points from experiments and the expectations from simulation are wildly different. And this is a clear example that either the model is incorrect or something is missing in the model. Maybe some things about the lines are not accounted or some interaction terms are not accounted. This is a model taken from the latest published cross-resonance model. So this suggests okay, but we can take a different approach here. We can treat the whole system as a black box and do a closed loop optimization. So in Q-Control for the Boulder, we have a pretty good setup for automated closed loop optimization, which you can do with this cloud-based quantum systems. So in there, we have the typical loop where you have the experiment and the agent, where you send some experiments to run and the results are sent back to the agent. We have a few diverse set of agents available. You can use Gaussian processes, neural networks, simulated annealing, or even reinforcement learning. So one key criteria to keep in mind while doing closed loop optimization on quantum computers, especially cloud-based quantum computers, is the fact that we have to minimize the amount of API kind of calls sent to the machine, because there is quite some latency when you say Qiskit.run. It has to go through quite some loops to get to the actual machine, and then the result takes quite some time to come back to you. So the way we approach this problem is we maximize the max number of batches allowed for running experiment in one go, and we change all the different parameters for which are the tunable optimizable parameters simultaneously, and essentially then we take the results from it, make the appropriate updates and send it and go in the loop. And all this process is completely automated. It's quite straightforward to use. The key thing is to figure out what action space you want and how to set up the cost function, which will go in a bit. And after that, all of it can just you just need to give it time to run, and that's about it. So the gate we are trying to optimize is a cross-resonance gate. This is the typical scheme in Qiskit pulse, which is the default pulse. And the key things we want to focus on are like, can we lower crosstalk errors? Can we have some robustness to frequency or amplitude drifts? Or another thing desirable is like, can we compensate for distortions in the signals? All these things we, in this closed loop approach, we don't need to explicitly define. The optimizer typically will take care of all those things under the hood. So a key important thing is to be smart about how we define the reward functions. So here I'm showing for reinforcement learning. So in that case, the cost is redefined as a reward function. In this case, what we are going to do in our action space is we will think about piecewise constant functions. So as earlier, like for any microimpulse, we have I and Q quadratures. So we'll think of two waveforms split up into 10 piecewise constant functions each, and that's our action space we want to optimize over. Each variable can take values between, say, minus 0.5 to 0.5, which is a typical range for AWG on Qiskit, I believe. Yeah, so for the cost, what we need to make sure is that we are not limited by spam errors. So just preparing some state and then doing one application of the gate and measuring would not give you a signal of like really small fluctuations in fidelity. So typically what we do here is we will prepare two initial states, in this case plus 0, so 0 plus and 1 plus state. And we will do a varying number of gate repetitions, and at the end of the sequence, we will do a two-qubit state tomography. The reason of two-qubit state tomography is that it tells you the purity of the state, also tells you if you leaked out of the computation space, which is important. And repeating it with more and more sequences lets you extrapolate to essentially zero spam errors. So, and this technique is much more efficient than randomized benchmarking for tune-up, because typically for randomized benchmarking, you would be doing same kind of scheme, but with random set of Clifford gates, and you would have to average over 20 different sequences. So this is kind of a much quicker way of getting the same information, because we only need a proxy for cost. We don't need exact cost. So by using that, what we get is, so this is the typical C0 gate. And in this case, as I mentioned, we only had tunable parameters for this pulse here as piecewise constant. We actually did not put any pulse on the crosstalk mitigation tone. So typically for cross resonance, you have single qubit gates on the control. You have some mitigation drive on the target. This is a single qubit drive. This is primarily there because there is crosstalk between the control channel cross resonance drive and the target qubit. So this is there to cancel it out. What the optimizer here does is it doesn't need this. It just figures out what changes it needs to do in the waveform to get cancellation of the crosstalk for the target qubit. Now on this axis here, on this plot here on x-axis, I have number of repetition of C0 gates. On y-axis is the infidelity. And here you can see that there is like almost a factor of 2 improvement in the error per gate for the default gates versus this deep reinforcement learned gate here. And the controls are much simpler. Now, this error is through repetition. One can do RB to check how it behaves. Here what we have is interleaved RB. So typically you do randomized benchmarking where you sample from 2-qubit Clifford gates, and you measure for longer and longer sequence of gates, and you measure what is the essentially infidelity in your system, and typically you see an exponential. Then what you do is you between every two Clifford gates you interleave a specific gate that you care about. In this case, we care about C0 gate, and then you get another exponential curve. In this case, it is much worse than the default curve. And the difference between the fit parameters tells you what is the gate fidelity for this specific gate. So in this case, what you can see is the purple corresponds to Q control's C0 gate, and the higher is better. So the triangles here are like much higher than this. In this case, it's like 20% improvement. And the key here is this kind of tune-up stays good even after 25 days. So in this case, you see that the dashed lines were what it was on the day it was calibrated. And after 25 days, we check again, and it's still better. Note that in this particular case, the black line is the gate calibrated the same day. So this is the default calibrated at that day itself. So even after 25 days of calibration, this reinforcement learning provided pulse is much better than freshly calibrated default. So we can do this for a different gate also. Swap is another gate which is often used in applications. So in this case, what we do is we explicitly tune up a swap gate where we use the standard decomposition of swap gate into 3 C0s, and then we tune up the C0 pulse here. But in this case, the reward to the agent is given based on how good the swap gate is. It doesn't know that this is actually a C0 gate in between. And here also you can see similar improvement, and here in RB it's also quite consistent that we see about 20 to 40% improvement in error. So this essentially highlights that closed loop optimization is quite useful for tuning up 2-qubit gates, which are typically very hard to tune up with model-based approach. And this is all automated, so it's quite easy to do it. Now I'll move to Boulder Opal part, where essentially I'll talk about algorithms and how the improvements which we get in single qubit gates or 2-qubit gates can be used, and on top of that we can build other improvements at circuit level to get better performance. Are there any questions until now? Okay. So for Boulder Opal, the goal here is we want to do all the system calibration without the worry for the user to know exact details of the device or how to mitigate certain things. So there are 4 key things about here where we want to do automated optimization of the gates at pulse level and keep them calibrated regularly. Can do also compilation where we are mindful of the crosstalk between different gates. Lastly, we want some measurement mitigation scheme that is scalable as we scale number of qubits, because traditional techniques don't scale so well. And finally, we would like to have it integrated in application directly. So how do we do a system-wide calibration in 4 steps? The way is you'll use the closed loop optimizers mentioned before. I'm showing a 2-qubit gate optimization. Excuse me. So this is a Guadalupe device. This is a 16-qubit device on IBM. So we split it up in 4 different groups. And the key is to make sure that you don't have nearby gates, because often what happens is you have to be careful that 2 neighboring adjacent gates can sometimes have crosstalk. So one way of avoiding that during your tune-up is to just not have those. And this kind of grouping, provided the topology is similar, is same. So you can do 4 steps tune-up for any size of device. So it can be 1000-qubit device and it would still take only 4 steps. And essentially what we do is we run for each qubit pair gate, we run a different optimizer in parallel. So all these things, all 5 pairs would be tuned up in parallel on the cloud. Next, we want to see how we can, what are the steps you would typically want to take in compilation. So let's say you make a quantum circuit, maybe in a CASM file. First step is, of course, you want to minimize the depth of your circuit as much as possible using identities or whatever heuristics available. Second is you want to map them to basis gates. For some devices, maybe there is no explicitly defined swap function. So at the end of the day, it will be compiled down to 3 C-naughts. Can we use those C-naughts with adjacent gates and reduce it further? So those things are taken care of. Here we primarily use TKIT, which is an open source compilation source package. And on top of that, we put some custom passes which take care of crosstalk. So this is where I was mentioning that we eliminate circuit level crosstalk. We note which qubit pairs when run in parallel have crosstalk between each other, and then we make sure that during compilation they don't occur in parallel and they go sequentially. And then we replace all the gates with the optimal pulses that we tuned up in the previous slide, and then we are ready to run experiment. And after the experiment, we would do error mitigation. So there are a few ways of doing error mitigation. The key is often accuracy and scalability. In this case, what I'm showing on the left side is a plot of so the default is essentially measured difference between 1000 random distributions generated on the device, a 7-qubit device in this case. How does the probability distributions of the measurements differ from the ideal distribution expected? In this case, the metric we are using is Hellinger loss. This metric is mostly taken because for algorithms, it translates in for certain cases to circuit fidelity. So this is one metric. You can take mean square error. It will just scale these things a bit. So in this case, if you just measured, even if you had like perfect single qubit gates or all your quantum gates are perfect, you just measure, this is the error you would see typically for the probability distribution. Now, a standard technique is to do a complete measurement mitigation filter, where essentially you create 2 power n basis states, and then you measure them, and essentially you get a linear map between what is the actual probability distribution for these basis states and what is the measure. And then you can inverse this 2 power n cross 2 power n matrix to get an inverse map and mitigate essentially from here to here. So it gives a good accuracy, but the issue is that, as it was obvious, that it goes exponentially in terms of the measurements required to calibrate such a matrix. Moreover, as we scale up, this 2 power n cross 2 power n matrices become really challenging and often ill-defined to take inverses of them. So this method doesn't really go so far, like beyond 7 qubits is really challenging already. Last year, IBM produced a very nice method called M3, where by doing only 2 power, only like a linear number of calibration experiments, you can mitigate measurement errors to quite some level. In this case, it does slightly worse than complete mitigation, but that's not surprising because it is not taking into account all the correlations that might be present there. So we are working on a new technique where essentially these are like preliminary results where essentially we can get similar performance as a complete measurement mitigation filter, but the cost or the number of calibration runs required to generate this mitigation are actually order of 1. It's just a fixed number of experiments required. Here I'm plotting them for n equals to 16. And this is something which we are really excited about because as we scale up, other techniques become quite challenging to scale. So now if we include all of those things which we have talked so far about different kinds of improvements, how do algorithms behave? Here I'm showing primarily like larger system circuits, so it's like 8 qubits all the way to 16 qubits. Black is what you would get if you just run, if you compile using the best methods available on Qiskit, and then you run the experiment, you measure the experiment results, and you plot on y-axis what is the success probability of this Bernstein-Vazirani algorithm. Just a quick reminder, in Bernstein-Vazirani algorithm, there is typically a secret string which you want to know, and so you go through the protocol, and at the end you measure the way we define here success probabilities. You're measuring what is the probability of the secret string coming up in the measurement. And here you can see that so the black is default and the purple is the Q control data. You see a pretty big improvement. And this improvement factor scales with as you go bigger and bigger in system size. In fact, like after this point, it's really hard to even see the black dot. And actually for the 16 qubit circuit in this particular case, there was 0 measured successful probability bit strings. Like there was no bit string that was measured, which was the correct string. So, but we can see with pretty decent chance what is the correct bit string if you do all the error mitigation. So this is where I want to highlight that control can really improve the performance of quantum devices right now. So it's not just about improving T1s and T2s, they are definitely very important, but we should also make sure that control uses the devices to the extreme as possible. So that's in summary, Boulder and Boulder Opel tools can really provide transformational improvement to the performance of NISQ computers. And model-based approaches, when you have a good idea of your model, can give really good robust gates which are stable for longer time and are insensitive to various fluctuations. Moreover, whenever we are not certain about some parameters in the model, we can use black box optimization tools which can be automated easily. So, any questions?
Yeah, thanks, Pranav. There will be questions. Yeah, Vijay, go ahead.
Yeah, hi, Pranav. That's a really impressive talk. I'm motivated to go read your papers now. I had a couple of questions in terms of general applicability of your methods. So, firstly, you showed a lot of results on the IBM system, which I'm guessing so you're using the pulse level access through the cloud. This is just a technical question. I mean, the fact that the machine is somewhere else and you're using fairly heavy pulse parameters going across the cloud. I mean, how much does it affect your optimization process? And I mean, is it a significant amount versus say you had a hardware sitting next to you and you could directly do this on that system?
That's a great question, and it is definitely one of the bottlenecks to quite some level. So this API lag is what I was alluding to here. Also, it is okay for like few gates. It's not quite noticeable. Like if you have like 5 gates you're running in parallel, we don't notice it so much. But I think as you scale devices up, say you have 1,000 qubits and you want to simultaneously tune up maybe hundreds of gates there. This will become a big bottleneck. So I think IBM has an upcoming thing called runtime, where you can run it. Basically, you upload your program on their server and you can run it there. Once it is like fully operational, I think that is something that can work. But I totally agree. That's a very valid point.
Okay, so just a continuation there is. If someone is working on hardware development, are your packages sort of can be adapted to work on individual people like experiments?
Yeah, actually, many of our customers are academic labs. So they like the package is very agnostic of the hardware, right? Like if I go to, I guess. This slide. I mean, this is the part that you need to change, which is essentially changing writing a wrapper to change the output format into the format that your lab tools would take. And that's essentially the difference. Like otherwise of course you have to choose your Hamiltonian and all those things, but that is standard for all problems. So it's like you can definitely use it for your own hardware in lab as well.
Okay, all right, thank you.
And typically we work like if some new platform comes up, we have pretty good team for supporting that, and we work closely to typically we'll work with our customers to provide a proof of concept notebook, which makes it much easier to run, and then from there you can work on the physics of it.
Okay, great. Thank you.
Okay, Sai, go ahead.
Hi, thanks, Pranav. Again, can you just go back to the slide where you had order 1 as opposed to order n? IBM? I was just a bit, so two questions I wanted to ask on the slide. One is that this mean Hellinger loss, is it comparable to something like diamond norm?
I don't remember the diamond norm formula off the top of my head, but essentially, I think Hellinger loss compares to.
Okay, I mean, I can look this up.
I roughly remember the mathematical formula, but I don't have a very good intuition for it in terms of metric.
Diamond norm tells you operationally. So if you perform, if you have 2 CP maps, it tells you what the distinguishability of the 2 CP maps is. So in that sense, it's really an experimental statement about, hey, if the diamond norm is really small, you won't be able to even tell them apart.
I see. So here, note that we are using probability distributions only. So no, only Z projections. And so this is truly a metric only looking at if we ran some algorithm and you expected certain probability distribution, how close is that probability distribution to what you are measuring right now?
So it's like calibrated blur or something.
Sorry?
it must be related to Kalbat-Lie blur then.
Yeah.
Actually, this is let me just ask the more interesting question, which is, so when you say that the number of calibration runs that you require are order 1 or even order 2n, this seems to assume basically that there is a hierarchy of stronger and stronger assumptions that you're making about what the noise model is, right?
Absolutely.
So what is the underlying noise model that you're just calibrating for local noise, so you can just stare at any one fixed number of qubits and you're done? Is that the
exactly? Yeah, that's essentially it. So what we are finding, and this is still work in progress. What we are finding is that if you choose the groupings carefully and you merge the data properly, that's all the info. Like at least on the superconducting devices, we don't see any other information needed for getting mitigation.
I see. Sorry, and just one last question. How many epochs typically do you run when you do, let's say, reinforcement learning or any of these other methods? Like how many before you run to convergence? How much time does your computer spend to?
That's a great question. So reinforcement learning is typically much much slower, because you have to go through we really start from no knowledge of the system. The other methods that we have, the simulated annealing or Gaussian processes, they typically take 6 iteration steps to get to the optimized solution. So we start with whatever is there in the default, because for paper, it's good to show, okay, you start from scratch and you can get to a fully tuned up gate. But practically, if there is a default gate already in the backend, we start from there, and then we optimize the basically that's the starting point, and then in 5 to 6 iterations, we always converge to the gates we care about.
And sorry, just one super last question. Do you have a grape implementation as well?
Grape implementation, we don't have it explicitly, but I mean, in terms of grape, but you can use the same machinery for that. We don't, actually, let me correct. I think there is a grape implementation in one of the tutorial notebooks online, but okay. You can definitely do it with the setup.
Oh, thanks a lot.
So Pranav, I have a question. These pulse shaping techniques, they have been used for NMR for many years, and they have learned all kind of tricks in the process. So for example, can you say that certain kind of universal gate sets are better than some other type? I mean, control knot is the standard example. Is there anything better available than control knot for a specific type of design or a hardware?
Right. Yeah, that's a great question. So I think for this specific set of devices, so the superconducting devices on IBM service, I think the control hardware is designed so that you can primarily cross resonance is your primary way of doing any gate. You can do off resonant ZZ gate, but that's much slower, and at least I think the current filtration scheme, I don't know exactly how what is the control chain at IBM, but doing some preliminary experiments suggests that it is not allowed, like in the sense that there are filters put in such that you can only do this control cross resonance gate. Now, if you take a step back from this particular architecture and then think more generally in superconducting circuits, if there are other architectures, well, there are certainly, I think in particular using tunable couplers, you can get ISWAP-like gates or swap gates, which are much better for certain fermionic simulations or those kind. So I don't know whether that's what you are looking for, or if you could maybe rephrase your question if I didn't
Yeah,
get.
no, that's a reasonable answer. I mean, I was just trying to find out whether the hardware designs assume certain kind of operations are much easily implemented than some other kind of operation, and you can tune your gates or complexity of the circuit according to that.
Right. So I think the key issue is often that when so we can couple superconducting qubits either capacitively or inductively. Those are the two key ways. If you have fixed frequency transmons, then coupling inductively is not very good. I mean, it's quite challenging. But so capacitively, if you couple, typically the dominating term is the cross resonance interaction, or the ZZ term if you do off resonant driving. But if you have tunable couplers, then many options open up. You can Google takes that approach kind of, right? Where you can have control Z gate, you can have swap gate, and the whole family of FSIM gates can be obtained pretty easily there.
Yeah.
I don't have a question, but I just wanted to say hello to Pranav.
Hi, Arinda.
How are you, Pranav?
Good. How are you doing?
Good. Enjoyed your talk. And are you in LA or in Sydney? Where are you located?
I'm in LA.
Oh, wonderful. Okay, we'll catch up sometime later.
Absolutely.
Okay, I think there are no more questions. So thanks a lot, Pranav, for this exciting talk. And well, we will remain in touch.
Yeah, thanks for the invitation.
Yeah. By the way, what happened to your that portable